second presenter. All right, Joseph, while you bring up your slides, I will introduce you. So Joseph Fisher is a doctoral student with Tim Simpson in mechanical engineering at Penn State and pursuing a master's in additive manufacturing and design concurrently. He's a graduate research assistant at Penn State's Applied Research Lab. He earned his Bachelor of Science and Master of Science in Mechanical Engineering with Stephen Shaw at the Florida Institute of Technology, where he modeled the dynamic response of micro-electro-manufactured lattice structures, including developing novel lattice topologies, testing of lattice properties, applying lattices to solve engineering problems, and developing a framework to guide engineers in the process of implementing lattices structures in application. With that, I will turn it over to you, Joseph.
Hi, is my audio working?
It is, and we see your slides.
Perfect.
Good to go.
So a lot of my graduate research has been really focusing around the design of lattice structures, which is a little bit outside the scope of what you talk about typically at these events with the SERC. But the framework that was mentioned at the end of my little introduction, we took inspiration from systems engineering models. So we thought it'd be great to bring this to the attention of some of the systems engineering group and get some feedback on how it flows. So in this presentation, we're going to go through kind of three main sections. We're going to talk about what additive manufacturing and these lattice structures are, some of the steps of the development of the framework, and then talk through the steps. And then we're going to apply the framework to a simple application so that we can give you guys an idea of what it is that this framework actually does. So very simply, additive manufacturing is a collection of these processes that build up objects layer by layer. So in order to do these types of things, you first need to have a digital model of your part. And then you can take that and digitally slice it into layers that you'll manufacture. And then you can go and build those layers one at a time using whatever process you like. And then you will end up with a final part that has been additively manufactured. And additive manufacturing, for anyone who isn't aware, is the kind of the industry term for 3D printing. They wanted a more formal term to talk about these types of things, but the terms are a lot of the time interchangeable. So I talked about additive processes. There are typically, in additive manufacturing, we talk about there being 7 processes. One of which will be applicable to our case study, is laser powder bed fusion. So the way this works, on the left, you can see a little diagram. You have a object or your part on your build platform, and you scatter layers of powder across very evenly and use a laser to melt the powder selectively to create your part. And then it drops down. You have another layer of powder come across, and it repeats until you have your whole part. And then a little animation showing you. So you see the powder gets spread across, the laser hits it, creates your shape, drops, new powder comes across, and it just repeats and repeats with whatever each individual layer looks like until you create your whole part. There's a lot of benefits that this offers. There we go. So you can produce really complex geometry this way, where with subtractive manufacturing, every time you add complexity, you're increasing your cost. With additive manufacturing, because you're choosing where you're putting material, it doesn't matter so much in terms of cost where you put it. It's up to you how you want to use it. So you can create some really interesting shapes. On the top left, there's a topology optimized bracket. In the middle is an additively manufactured Stirling engine that I produced for one of my courses. You can create some very interesting brackets. Autodesk did a generative design on quadcopters. You can see that in the bottom left. And then there's applications in heat exchangers where you can really tailor the design, not to how to create something out of manufacturable materials, but really based on what you want to create. And then in the bottom right, you can see a very complex lattice structure wrapped into a Mobius strip type geometry, which is pretty neat. So that's additive manufacturing in a nutshell. So what are these lattices that I'm talking about? So like engineered foams that you can see on the left there, these are a type of cellular solid, but they're very highly ordered. So where the foams are very chaotic, the lattices are very organized. So you take, so there's 8 different unit cells on the right on the bottom there. You can take any of those or any of the many others, and you can pattern them through space infinitely to produce a lattice structure to meet the size requirements of your part. So you have these structures that are a lot more predictable than foams locally, which is an added benefit when you're dealing with trying to predict their properties. So why do we care about these lattices? Main reasons are it can make parts lighter, and it can reduce the cost of implementing additive manufacturing, and potentially also improve the performance of these lattices. Some other additive geometries on there. On the left is a little heat exchanger designed by Entopology. In the middle, you have the bus assembly for a CubeSat, where it has been filled with a gyroid lattice structure to reduce the weight and increase the stiffness. And then an optimized lattice structure on the right there for a fairly simple bracket geometry. So I showed 8 different lattice structures, but really there are almost an infinite number that you can choose from. In a practical sense, there's probably about 100. But once you've chosen a lattice, you still have a lot of decisions left to make, which is where our framework is going to start coming in. So you have to choose, once you choose what cell type you're using, you need to figure out what size the cells are going to be, what aspect ratio they're going to be, because that can affect your properties significantly. If you imagine the middle row there, if you were to compress them in kind of the vertical direction of the slide, they would all perform quite differently in that respect versus if you were to squish them sideways. And then you also still have to choose how much material is actually going to go into the lattice and where and what orientation those cells are in. So there's still a lot of decisions to make, and I think that there's a lot that our framework can do to help address these. So the goal of this framework that I'm proposing is to add kind of a structure to making these lattice decisions. So it should be easy for people to understand and follow. We want it to be driven by requirements rather than engineering intuition, where a lot of decisions in lattice design are there right now. We want it to be independent of the material and the process that you choose. So we said there were 7 additive processes. We want it to be able to be applicable to any of them and any material you choose to use with that process. And then other important aspects are we want to include verification and validation of the design into this. That's something that's overlooked a lot of the times when designing with lattice structures. And it should be extensible in that it shouldn't limit the creativity of the designers, and it should be applicable to multiple design techniques of lattices. So we're not saying everything that in lattice design that's been done is no longer relevant. We're saying that it's all very good, but you really need to have it in the frame of requirement-driven design if you want to use it on complex systems and things like that. So the reason why we chose to draw from systems engineering and from system design for our framework is that we saw a parallel between a system that is built up of subsystems and components and a component that has had a lattice integrated into it. We see those as subsystems and then essentially the components that build up the component. So the cells of the lattice collectively produce the performance of the component itself. So we see that as like a system within a system. So for that reason, we looked at system engineering for our inspiration. We explored several different system models that have been proposed, but we found kind of the system V model to be most applicable to what we have in what we want to approach from. So really it has a strong emphasis on the hierarchy. It has a requirement flow down very well emphasized, but it also includes integration and the verification and validation. So we felt that this was a really good place to start when defining our framework. So we have kind of three key ways that were either similar or dissimilar from some implementations of the systems V. So we have on the left, when we do planning, it's directly related to verification and validation on the right side of the V. The Lattice V, or the LVF, as I may be abbreviating it through the presentation, is a lot more prescriptive. So whereas the system V is very general about what types of things you should be doing, the Lattice V can be very specific about what you should be doing when, and that relates to it being a much more concise problem that we're trying to solve, and also that it acts on a much shorter time scale. So the implementation of the Lattice V is the design of one component of a system. So inherently, it's going to operate much more rapidly compared to the design of an entire system that it's integrated in. So now, starting to actually talk about and show the framework a little bit. We group the steps kind of into three sections, where you're working through the decomposition of the component, where you're determining what it is that the lattice needs to do for you. At the bottom, you're implementing the lattice, and you're determining where the lattice is going to go and what it's going to look like. So that's really where the kind of the rubber meets the road of designing the lattice. And then you're going to integrate the lattice and integrate it into the component and determine if it meets the requirements set. We rely on three kind of primary assumptions: that you already know your material and AM process. There's no steps within the V that are going to help you determine that. But we found that most people already have an idea of what material and what process are relevant to producing whatever it is that they need to produce. The second assumption is related to that you are actually able to produce the part with that process. So you're not going to try to print an entire airplane in one piece on a printer that is, say, like a foot by a foot by a foot. So if you know, you want to make sure that it's possible to even print the part. And then the last is that you have properties of lattice structures that you can use to make the decisions you need to make. So if you're trying to do the design of a heat exchanger, you'll need information about the thermal properties of the lattices, how they transfer heat differently. And if you're doing a structural problem, you need to know the different mechanical properties of the different lattices. So I'm going to kind of walk through in kind of three chunks the steps of the V. So you start with requirements that flow down from your system level design, and through an analysis of your component, you're going to determine what we call the localized requirements. These are going to be used to drive the design of the lattice. And as you go down, you need to plan both at the component level and at the lattice level what your verification and validation is going to look like. So you need to plan ahead so that you can actually then perform these tests. We find that a lot of the times people wait until the end to figure out how they're going to verify and validate their component. And by forcing people to think about it sooner, it improves the quality of the design. Second, we have the actual implementation. So you're going to define the lattice domain based on the localized requirements. So you're determining, where can I put lattice? Where does it need to be solid? Either based on what the requirements say or what performance is needed from the lattice. Next, you'll use the range of properties you need to determine what unit cell you're going to actually implement. And then finally, in the lattice cell definition, you map out your cells and you propagate them through space. On your way, as you start to move back up the V, you're going to check to make sure that those lattice cells you defined are actually manufacturable using your process. And then we can move to the rest of the integration with verification and validation. So you're going to apply a homogenization technique, which I'll talk about a little bit more in the example, to make sure that you're meeting those localized requirements. Then the lattice can be integrated, and then that can be integrated into the component, where you can then follow out your verification and validation plan. So this V process, the goal is to start from component requirements, go all the way down and back up, and end up with a component that you verified and validated against those initial requirements. So we can jump into the example problem. So we're trying to redesign this component here that was already previously designed with a lattice structure by a previous author. But they used a very intuition-based approach. So we're going to see, can the lattice V help us to do a better job at designing this? So simplifying the problem just a little bit to make it easy to discuss here. We're just looking at a minimum factor of safety. The outside and internal surfaces are pressurized, and those have minimum thickness based on the specifications for the part. But that leaves us the rest of the space to kind of work with our lattice. And then we have a specified material for chemical compatibility and a process that we can use. So we meet the requirements and the assumptions in order to apply the V. So we're good to start. But first we need to think about the limitations of the additive process we've selected. So we're going to frame it as 3 primary limitations that are relevant to this one. So we have the ability of the AM process to create these unsupported bridges, either arching or flat. The flatter you are trying to build over empty space, the trickier it often is with additive manufacturing. So we've defined limits on what we think are applicable for our process. There's a minimum size that we can print based on in this case, the size of our laser and the size of our powder. So we can reach about a 0.5 millimeter without losing the integrity of the design. And then we can also print overhanging angles. So as you approach closer and closer to flat, the difference between an overhang and a bridge is is supported on 2 sides, whereas an overhang is only supported on 1. So what happens to that free edge? You can see that as you approach smaller and smaller angles, it gets pretty ugly. So what we say that about a 40-degree angle is what we're comfortable with for our design. So the design we come up with will be checked against these in the manufacturing verification step. So we use the component requirements. So we have pressure, as you can see on the left, applied to the outside surface. And then there's also these 2 interesting little interwoven fluid channels that pass through it. Those are pressurized also. So we use those to define a finite element analysis simulation, which we then use to define what we call the lattice level or the localized requirements. Based on the minimum thicknesses we were given, we can define the domain of the lattice, which on the left is the area that's in purple. We're looking at the component cut in half, so you can see some of what's going on inside. But it is symmetric, so there isn't too much more to see on the other side. We then can, based on our localized requirements, we can choose an appropriate lattice. The data to do this is fairly sparse right now, but that's one of the things that I'm working on, is trying to get better lattice data. But based on what's available, we're choosing a lattice called the gyroid. In this figure, it's called the TPMS gyroid, which is triply periodic minimal surface. But it looks like the shape on the bottom right there. So we know what our lattice is, but we still need to define a lot of the other things about it. So we're going to go with a nice cubic unit cell, keep things very simple, and a volume fraction of 12.8% should meet our localized requirements in the domain of the lattice. And then we can check and see if this is manufacturable. It is. The arches are less than 45 degrees and the overhangs are sufficiently small for it to be printed. And our minimum feature size is above the minimum that we can print. So we're good in terms of manufacturability. And then we can go and apply homogenization, which is an approach where you simulate 1 unit cell of the lattice, and you can get the directional properties, and you can use that. You can apply that to a larger volume, and instead of having to simulate each cell of the lattice, you can simulate material that represents what the lattice properties should be globally. So we apply homogenization, we can compare that to what we think the localized requirements are required to be. And then we can, the minimum properties of the lattice met what we expected. So we're good to integrate. So we can integrate it and then do a full FEA of the design. the goal of the homogenization is to try to catch problems before you have to go and simulate the entire component, because these are very, very small and very fine structures. So you have to have incredibly large mesh counts in order to accurately simulate them at the full scale. So to try to wrap all of that up in one slide, so the Lattice V framework is an extensible framework for kind of bridging the design methodology at the system level with the design of lattice structures at the subcomponent level. It fits within some of this existing engineering design practices, and it tries to balance being prescriptive of telling people what they should and shouldn't be doing with being extensible so that it can be applicable to multiple regimes within lattice design. And then there is ongoing work of trying to generate more data through both experimentation and FEA, producing a cleaner tool chain to demonstrate how this can be implemented, and then building out additional case studies similar to this one to show different aspects of the V. Thank you. And I have a paper from a recent conference on this topic that goes into a bit more detail if you're interested in taking a look.
Thank you, Joseph. Do we have any questions for Joseph? I have one question. So you talked about the V model. What were the other models that you looked at before choosing that one?
Yeah, let me see. I did not include it in this. But we looked at things. So like, obviously the first thing we looked at was the waterfall model, because it's the simplest and they teach it in like engineering 101 as the start of everything. We looked at that. We didn't like that there really wasn't a coming back together. So the integration, like it's obviously in the model when you integrate your stuff together, but it's not a huge focus. We looked at the spiral model. There was an awful lot going on there that because of the short time scale of the lattice design, it wasn't directly applicable, because there's a lot of really good information about things that are more on the planning, and then a lot of the steps that go into the design. And then I think we looked at one or two others, but it's escaping me at the moment.
Nope, that makes total sense though. Any other questions for Joseph? All right. Well, thank you so much. And we're ahead of schedule, so we're moving into the break and we will resume at 12:40. Thank you, everyone.